the next example asks us to calculate the flux of the field F equals zk through the surface S, that is the upper half of the spherical surface rho equals 2. So in this case, our vector field only depends on z, and it points straight up and is equal to the z component, so that it's shorter when it's lower and the vectors are longer when they are higher up. And we want to know, what is the flux of that vector field through the surface? Well, there are a couple different ways to approach this problem. I'm going to start by letting z be the square root of 4 minus x squared minus y squared. So that is a sphere of radius 2. And by taking the positive square root, I'm just getting the upper half of that sphere. And then f in rectangular coordinates is 0, 0, z. Well, my normal vector then is minus the derivative of z with respect to x. So that turns out to be minus 1 over root 4 minus x squared minus y squared times a negative 2x. And then, similarly, the negative derivative with respect to y is again 1 over 2 root 4 minus x squared minus y squared times a negative 2y. And then the z component is 1. Because we're going to do f dot n as part of our surface integral, then f dot n is just going to be z. And so that can be written as square root of 4 minus x squared minus y squared, because we want to represent z as being on that surface of the sphere. So if we want to compute the flux of f dot ds over our surface, well, that's going to be a double integral over, and then our domain for the sphere is going to be just x squared plus y squared is less than or equal to 4. And then we're going to do f dot n dx dy. So in this case, we're going to do the double integral over that circle, or that closed circle, x squared plus y squared is less than or equal to 4, of f dot n is the square root of 4 minus x squared minus y squared dx dy. Now it should be apparent that actually doing that integral is simpler if we do it in polar coordinates. So here we can describe that circle as the integral from 0 to 2 for the radius, and then the integral for 0 to 2 pi as theta. And then I'm going to do the square root of 4 minus r squared, and then that's times r dr d theta. Now at this point you can do a u substitution where you let u be 4 minus r squared, and then you can compute this integral. I'm going to leave the details to you, but you would get 16 thirds pi. So as I mentioned, that's actually just one way. And the method here was because the vector field was described in rectangular coordinates to go ahead and describe the surface in terms of rectangular coordinates. Okay, but this surface itself is given in spherical coordinates. Okay, so maybe it would make more sense to do this in terms of spherical coordinates. So for this alternative method, for the sphere, I want to point out that the unit normal to the sphere is always going to be the vector xyz divided by the length of xyz. So the unit normal for the sphere points outward in the directions x, y, z, and then I need to divide by the length of n, which is the square root of x squared plus y squared plus z squared. So what that means is that if I compute f dot n, my unit normal, then I will get just z squared, okay, because I'm going to dot xyz with 0, 0, z. I'll get z squared divided by the square root of x squared plus y squared plus z squared. But if I want to stay on the surface of the sphere, that sphere is where x squared plus y squared plus z squared is equal to 2 squared. So in fact, this is going to just be z squared over 2, okay, on the sphere. Okay, so rho is in fact the square root of x squared plus y squared plus z squared. So if we're going to stay where rho is equal to 2, okay, then f dot n in this case is going to be z squared over 2. Well, if I now want to compute the flux, I can do the double integral over the surface of f dot n ds. And so this is the double integral over the surface of 1/2 z squared ds. And now I'm going to describe this surface in terms of spherical coordinates. So I'm going to do this integral ds in terms of spherical coordinates. In this case, I'm going to have 1/2 times z squared. So z is going to be rho, which is 2 cosine phi squared. So here I'm using the fact that z equals rho cosine phi, but rho, if I'm on the surface, is 2. And then the ds is going to be rho squared, 2 squared, sine phi. Okay, so this here is rho squared sine phi, but again, rho is 2. And then I would integrate d phi d theta. Okay, this is going to be the top half of the sphere. And so phi is only going to go from 0 to pi over 2, and then theta is going to go from 0 to 2 pi. Okay, now this is a double integral, which you are capable of computing yourselves. And so if you do that, you will again get 16/3 pi. Okay, so this is 2 different ways to compute the flux through, again, the upper half of this sphere, okay, if my vector field is 0, 0, z, or z times the k direction. Let's now move to one more example. Okay, the last example is to calculate the flux of the vector field x, y, and 4z through the surface S, that is the solid bounded by the cone square root of x squared plus y squared, and the plane z equals 3. So what I've done is I've drawn the cone, and the cone is actually going to define two surfaces that we're going to be interested in. The first one, surface 1, is just going to be the plane z equals 3, and then the second surface, 2, is going to be the surface of the cone, z equals square root of x squared plus y squared. So for the first surface, it's going to be easy to define the normal vector. The normal vector in this case is just going to be 0, 0, 1. Okay. Actually, that's going to be the unit normal vector. And so f dot n in this case is going to be 4z. But if we want to be on the surface, so if we want to evaluate f dot n on the surface, z equals 3, then in fact f dot n in this case is going to be 12, 4 times 3. So the flux through surface 1, so integral of f dot ds over that first surface, surface 1, okay, that is going to be the double integral of f dot n, which is 12. So this would be f dot n, which we know to be 12, ds. And then I can describe the ds any way I like. So because it's a circular region, okay, I'm going to describe it in terms of polar coordinates. So I'm going to go the integral from 0 to 2 pi for the thetas, the integral from 0 to 3 for r's, f dot n is 12, okay, and then the ds in this case is going to be r dr d theta. Now, if you go ahead and compute this integral, it's again a pretty simple double integral. You will get 108 pi. Okay, so now let's look at the second surface. For the second surface, I'm going to define the normal vector as being minus the derivative of z with respect to x minus the derivative of z with respect to y, and then 1. So here, I'm going to get minus, okay, the derivative of z with respect to x is 1 over 2 root x squared plus y squared times 2x, and then minus 1 over 2 root x squared plus y squared times 2y, and then finally 1. But notice that this normal vector is actually pointing inward. Okay, but I want to think about the flux going out of the cone, okay, and that means I want the normal vector to point outward. But it clearly points inward with those negative signs. So what I'm going to do is I'm going to, so this is the inward, I'm going to do the outward normal instead by multiplying by -1. Okay, so that's going to give me just x over square root of x squared plus y squared, y over square root of x squared plus y squared, and then 1. Okay, so now I would like to compute f dot n. Okay, let's recall that f is x, y, 4z. So if if I dot x, y, 4z with n, I will get x squared over square root of x squared plus y squared plus y squared over square root of x squared plus y squared plus 4z. Actually, minus 4z. I forgot I had multiplied this by -1, so this has to be a negative. So minus 4z. And now I want to simplify a little bit. So I want to do f dot my outward normal vector on the surface of the cone where z is equal to the square root of x squared plus y squared. Well, x squared plus y squared over square root of x squared plus y squared, okay, that's going to be just square root of x squared plus y squared. And then I'm going to have minus 4 square root of x squared plus y squared. So in fact, this bit here simplifies just to square root of x squared plus y squared. So square root of x squared plus y squared minus 4 square root of x squared plus y squared is going to be -3 square root of x squared plus y squared. Okay, so now we have f dot n, and we just need to do our integral. Okay, so we have the integral of f dot ds to give us the flux. That's going to be minus the double integral. Again, over that circular region, x squared plus y squared is less than or equal to 3. And that's going to be 3 times the square root of x squared plus y squared. This will be dx dy. So hopefully at this point, you will be able to see that the best way to describe this is to describe it in terms of polar coordinates. So I'm going to do minus the integral from 0 to 2 pi, and then the integral from 0 to the radius, and the radius in this case, okay, is going to be, well, this is, okay, this is the issue here, okay. This is x squared plus y squared is less than or equal to 9. Okay, so that the radius is between 0 and 3. So if I go back, see I have z is equal to the square root of x squared plus y squared. So this intersection right here is where square root of x squared plus y squared is equal to 3. So that should be x squared plus y squared is equal to 9. And so that gives us that my circular region is x squared plus y squared is less than or equal to 9. Okay, then this integral in polar coordinates would be minus the integral from 0 to 2 pi for theta, the integral from 0 to 3 in r. We're going to integrate 3 square root of x squared plus y squared, so that's r, okay, times r dr d theta. So essentially, we're going to integrate 3r squared dr d theta. Okay, this is again an integral I believe that you can do, and so we will get -54 pi. So the flux through that part of the cone is going to actually be negative. Okay, so if we want to look at the total flux outside of the closed cone, okay, so the total is going to be the flux through the first surface plus the flux through the second surface. Okay, so that's going to be 108 pi coming out of the top, but then negative 54 pi going through the edge, the surface of that cone. And so the total flux is going to be 54 pi.